let's see. The first one is more evil than it seems because the most common mistake is to forget this is not equal to cosine, right? What's wrong with that? Because the derivative of cosine is not sine, yeah. So it's negative. So that's one of the worst things, is trying to change gears between differentiation and integration. It's going to be the opposite of what normally happens. And you can just always check, just kind of take a real quick check when you write something down, quick derivative in your head, and see if it needs an adjustment or not. That one did. So now it's negative cosine pi minus negative, so plus cosine of 0. What's cosine of pi? So negative negative 1 is 1. Cosine of 0 is 1. So you get 2. And visually it's nifty. Here's sine from 0 to pi, right? That's pi over 2, that's the next one. So this area of that dome is 2. That's kind of nifty. That's what we just figured out, right? The area under sine from 0 to pi. That is kind of nifty. Unexpected. Maybe. Because, like, I had 0 expectations. B, slightly better marker. So this one is, again, I try to hit you several times over with the common mistake stuff. One little thing, I don't know if I've said this properly, I'm pretty sure I did a while back, but you could take constants in and out of integrals. It's because what are integrals, really? Remember, basically, what are integrals? Don't tell me areas. What are they built off of? The building blocks. All the ugly thing we had to do before we learned the shortcut. They're built off of
Derivative.
what is it? Where did this symbol come from? Where did this symbol come from? That came from delta x. This came from the limit as n goes to infinity of a sum. So that's why it's a big ass S, because integration is basically summing. And if I take a 2 out, I'm just factoring a GCF of 2. That's all that is. That's why a constant can come in and out all day long. You can never take an x-related thing in and out. That doesn't make any sense. Because that is what this thing is built on, is x stuff. And x is the thing that changes, so it's not a common factor. It's constantly changing, but this is always frickin' 2. So if you need to, you can take the 2 out of the way. That's the short answer to that whole one. And what's the integral of 1 over x? Yeah, ln of the absolute value of x. So now this is 2 ln of 1, right? Minus 2 ln of 4. What's ln of 1? 0. And then you just get that. And if you plug 2 over x in your y1, graph it. Second calc, number 7 is integration. Tell it from negative 4 to negative 1, you can check it. They'll give you some decimal, and then you go back and you do this and make sure that they're the same. That's how you can check your integration work, your definite integration. Indefinite integration, too damn bad. Can't check that shit. Except through derivatives. Is that so far so good? How are we doing there? All right. C. Oh, yeah. So we just done one like this, but this guy doesn't need an adjustment. I know it's going to be related to 3 to the x. This guy's derivative is this. So that's the integral. And then I have to evaluate that from 2 to 3. You guys see that? It has what it needs right there. It's not missing anything. If that wasn't there, then I have to divide this by ln3 because it would have died. Did it die? No. I don't need an adjustment. Does that make sense? What is the derivative of 3 to the x? 3x ln3. So what's the integral of 3x ln3? 3 to the x. Okay, maybe. It's sort of the difference between the integral of x squared versus integral of 3x squared. Which one's easier? Sort of. This one, because that 3 is exactly what would have come down. So I just put them back together, x cubed. This one, he's missing a 3. Let me, real quick. Sorry, I know I do this all the time, but what do you wish was here? You wish there was a 3. If I put a 3 there, I have to put a 1/3 out there. This is really a cool idea that we're going to use a lot later. Giving it what it's missing, balancing it out. I just overall did nothing. Yay, Jeff. But then what's the interval of this? X cubed. The 3 just goes back up. And then that's another way to look at why the 1/3 is there. Because to put what I need there, I have to balance it with the 1/3 on the outside. That's another way to look at why it's there. Okay, you guys are like, I don't like either way of looking at it, Jeff. Shit. All right, so what do you get here? How do you do this? Yeah, you get 3, put 3 in, 3 cubed, minus 3 squared, 27 minus 9, 18. And again, you can throw that in y1. Second calc, number 7 is integrate, 2 to 3. Check it. That was nice, it's 18. Yay. Okay. You probably didn't expect that, but it's because this had what it needed and made it easy. All right, this guy. First off, this isn't really theta. It's phi or phi, depending on how you feel. Feel phi phobe. When you integrate this, it's just like the first one on one level. It's definitely going to be just like we got on the first guy, negative cosine. But what do I need? What needs an adjustment? If I just stop there, a pi would pop out. Is there a pi here? Pop, pop, pop. So one again, you could either say, okay, 1 over pi to put the pi that I want there, or you could say a pi would want to come out. I got to kill it. Either way, I have no preference at all. They're both beautiful. Evaluate that from 1/2 to 1. So I get negative cosine of pi, putting a 1 in, divided by pi, minus negative, so plus cosine of pi over 2. And of course, cosine of pi over 2 is 0. Sweet. Cosine of pi is negative 1 times negative 1. So you get 1 over pi for that one. And again, put in a y1, do the integral, blah, blah, blah. You can check it on your calculator. Okay. So part E, this is yummy. This would have been much easier if I would have said 1 to 2. Because this is always positive, I can just take the absolute values away. But it includes parts where it's positive and negative, that's why I've got to break it up. Where's this thing change from positive to negative? At 1/2. So I've got to break this up, 0 to 1/2, 1/2 to 2. Now, below 1/2, what kind of number is this? So like if I put a 1/4 in there, I get 1/2 minus 1, that's negative. So that's where it's going to have to change the sign. Over here, it can just stay the same because up in that area, it is positive. So I can just leave it alone. Well, I can't. Same thing you would do with the explicit piecewise function. This is an evil implicit piecewise function that you have to realize. It's true. So here, how do I integrate this? This is really nice. X minus, the 2 goes back up, x squared. And that's evaluated from 0 to 1/2. And then this is the same thing, just turned around, right? Plus x squared minus x, evaluated from 1/2 to 2. And then you just got to plug that stuff in. This is nice. There's a 0 that kicks ass. All right, there's nothing weird here, just x's. So 1/2 minus 1/4 plus, when you plug a 2 in, you get 4 minus 2, 2. And when you plug a 1/2 in, you get 1/4 minus 1/2. Now here's a really good reason why you don't mess with the ugly parts. Fractions aren't that ugly, but do you see what's going to happen? Yeah, that dies, and that dies, and everybody dies, except for 2. Wait, so what happened there? 1/4. Oh, I see what I did. All right. So what did I do there? What mistake did I make? I made a mistake right here. I made, rookie mistake. So I put the 2 in. 4 minus 2 is 2. And then what should be here? Minus. I like it. So that's minus, now I can do this. 1/4 minus 1/2. So these don't cancel. Cool. So these actually, 1/2 and 1/2 makes 1, and 2 is 3. And then 1/4 and 1/4 makes minus 1/2. That's better. And then I get 5/2. Cool. All right, that was E. Now the only difference between the first section and the second section is, what do I have to put in there in the second section? What do I have to include in those?
C.
The plus C. I like it. These, if I would have put plus C, they would have canceled between. So that's why we don't even bother with it. But here, you're working better. So when I do this, so how about this guy? What's this go to? Yeah, the power goes up because we do the opposite of differentiation. And then instead of multiplying by power, I divide by that new power. So it really just becomes negative that. And then this guy, of course, just becomes 3x. I like it. And then plus C. Cool. That's not too bad. It's just the power rule there. What about part B? Oh, yeah. Somebody asked about this earlier, which is kind of funny. Be careful now. Don't put pi x. Doesn't make sense for this guy. What's this going to be?
T.
Pi t. Pi t plus c. Bam. And then what do you have to do with part C? Same thing you have to do with part D. Same idea anyway. I love you guys. Some of you guys are like, I have no idea what to do with this shit.
Well, you do trig identities first before you do anything, right?
Well, okay, what kind of identities do you mean?
Well, because tangent equals sine over cosine.
Beautiful. All right, I love it.
Times 1 over cosine.
Beautiful. So you get sine over cosine over 1 over cosine. So, of course, the 1 over cosines cancel. So it's really just integral of sine, which by now you should know really well is,
Negative cosine.
yeah, do you see how many times it showed up on here? Do you see how I'm trying to put this together to give the most common mistakes and get them out of your system now? Integral sine is negative cosine plus c. So we're going to learn more complicated, we're going to learn advanced techniques of integration for when the inside is more complicated. But you don't immediately go to those. We just did something that looks disgusting, but it looks a lot better once we actually just simplify the damn thing. Same thing with the next one. I don't have to use anything more complicated than just power rule because I can simplify this down to power rule. So this would be x to the 7/3 minus 4x plus 2 over x squared. So what's this become when you break it up?
X to the 1/3.
Yep, 1/3 minus 4 over x plus 2x to negative 2. You can write it however you want to. I decided to do it both ways. Just because I think 1 over x more than I think x to the negative 1. Right? Where does that go to? Just do that piece first. 4 ln. Absolute balance, I like it. This guy.
3/4.
Ah, I like it. Okay, so x to the 4/3, and the shortcut is 1 plus 3 is 4. You add 1 to the top, and then you divide by the new power, which is just multiplied by the reciprocal. Kick ass. And of course, this last dude, yeah, it would go to x to the negative 1, divided by negative 1 makes it negative 2. Let's see. I like it. So really, all of these problems we're doing could have shown up, or probably did show up, something like this back in section 4.9, because this truly is just anti-differentiation. This is the stuff where we linked the antiderivative with the area. This is the big new stuff, to be honest. This indefinite interval stuff is section 4.9. Okay, so let's focus on this. So here's, I think I asked you this already. Who remembers anything about partial fractions? I mean, you're like, I'm not going to say I do, because then you're going to ask me shit about it. And no, I won't. I just want to see. Has anybody ever heard of partial fractions at least? Yes? Tell me everything you know. So real quick, help me out. What is 1 over x minus 1 plus 2 over x plus 4? Do that. Yes, Jeff. Give me a lot of these on the test, please, your dot Jeff. This is not partial fractions yet. This is a very straightforward Math 90. Do it. So yeah, when both denominators are missing each other, yeah, it's an application. It's a creative use of cross multiplication. It isn't really that, but that times that x plus 4 plus that times that 2x minus 2 all over both. So then you get 3x plus 2 over this. So what partial fractions tries to do is it says if I start here, I want to know where that came from. I want to tear that thing, tear it apart. I want to tear it back apart into its parts. All right? So that sounds, I don't know, that might sound easy or hard. I have no idea, especially if you haven't ever seen this. But what you do, where's the only place that, I'm not sure what I should do here. Should I start with that one? Like if I had 4x minus 1 over x plus 2, x minus 3. What would it look like where it came from? Where would it have come from? Look here. Where did that come from? It came from a piece over x minus 1 and a piece over x plus 4, of course. So what would the form of where it came from be? Something over x plus 2. Let's make it a little more formal. A over x plus 2. And something over x minus 3. B over x minus 3. And, well, we'll get into that later. Basically, the top piece will always be 1 degree below what the true bottom is. I said that in a very strange way. You'll see what I mean in a minute. You guys see how the top is constant, the bottom's linear. That's off by a degree. If the bottom was x squared plus 2, the top would have to be the most general first degree, which would be ax plus b. You always have to be off by a degree. All right. So how the shit do I do anything with this? What are my true parameters here now? Let me use the right word. It's not really variable. What are my parameters for this? Do I give a shit about x? X is my variable. But x doesn't matter worth shit here. I care about a and b. Right? So how do I solve this thing? Well, you solve it the same way you solve any equation like this, really. You make everything the same denominator and then multiply by it. But hopefully we're to the point where if I multiply by this side becomes this. X plus 2 cancels, so the a picks up x minus 3. And the x minus 3 would cancel for that guy, so the b picks up by x plus 2. So if you put that next to each piece, multiply both sides by it, that's what would happen. And now we do something called equating coefficients. Now you could, let me show you. So I'll show you the other way in a minute. I'll show you another way to do it. This is not that bad. This is where people, I think, were like, I remember that shit, but man, it leads to disgusting, big, ugly stuff. Not always. There's a way you can do this. Almost always you can do something to avoid like a 5 by 5 matrix of shit. But this way, real quick, this is the standard textbook way to do this. Wouldn't it be ax plus bx, right? So I got a plus bx. Is that cool? And then it would be negative 3a plus 2b. So equating coefficients, that is inequality. That is a true statement. Therefore, a plus b has to be what? A plus b is where? In front of the x. So a plus b has to be 4. That's why we call it equating coefficients. In order for this equality to be true, the coefficients of all my x pieces have to be equal. So a plus b must be 4. And negative 3a plus 2b has to be negative 1, the constant piece. The x piece coefficient has to equal the x piece coefficient. The constant has to equal the constant. If there was x squared, it have to equal x squared, so forth. And you get a little, system of equations. All right, multiply this by 3. Add these, you got 5b equals 11. That's yummy. B is 11/5. A plus b is 4, so a has to be 4 minus this. All right, so 4 minus 11/5 would be 9/5. There you go. Jummy. All right, let me see if I can push this a little bit. So this means that if I had this question, and of course, more than likely, it would start off with this not factored. Ooh, so you just factored the damn thing, right? I can rewrite this as the integral of 11/5 over x minus 3. So 11, let me see what you guys can handle. 5 x minus 3 plus 9/5 x plus 2. So 9/5 x plus 2. Now, help me. Ignoring the 11 and the 5, what's the integral of 1 over x minus 3? What's the integral of 1 over x minus 3? Because if you wanted to, what you can do for yourself to make this look a little better is take an 11/5 out of this piece and a 9/5 out of this piece. So you can really focus on the x part. Now, please, what is the integral of 1 over x minus 3? ln x minus 3. Why is there no concern about pieces missing? Because it's a linear with slope 1. So it's the same as if it was x. There's no chain rule piece to worry about. You guys get that? What's the interval 1 over x? Ln absolute value of x. What's the interval of 1 over x minus 3? Ln absolute value of x minus 3. There's no chain rule piece to worry about. It's a slope of 1, linear. It's not going to do anything freaky. But see, that's what partial fractions does, is it takes this thing which is impossible for us to do. There's no u sub going to save your ass here. And breaks it up into 2 pieces that I can do both. Or 3 pieces, or however many pieces it needs. So this would be 11/5 ln x minus 3 plus 9/5 ln x plus 2. Plus c. So now, with what we've discussed so far, you should be able to do part E on number 2. Go ahead and do that, and then I'll talk more about other partial fraction stuff. Let me go ahead and give you this. This has got more than what we've talked about so far, but the first one is just like the one we just did. Oh, yeah, that's right, I forgot. Here, guys, real quick, before I go too far away. Right here, there's a whole other method that I prefer. Maybe not on this one. This is so silly small, who cares? But this is a little bit freaky, but it's going to help when you get worse partial fractions. What is x in this whole thing? What is x in this whole thing? What is it? Anything it freaking wants to be, right? Because where did this come from? It came from this statement, this expression. So what is x? Anything it wants to be except 3 and negative 2, right? Bless you. But in this equation, could x be 3? Yes. So watch what I could do. Watch what I could do. If x is 3, what happens to this side? It becomes 11, right? So 11 equals, why did I pick 3? Because that makes that go away. 11 equals 5b. So what's b? Freaking 11/5. So this is the standard way it's shown. Sometimes people just skip over this other way of doing shit. So then how do I get a? Well, I let x be negative 2. Do all the same thing I just did. You got 9/5. Much quicker. Can you always do this? No. Because if this was x squared plus 2, I'd have to make x what? I rad 2 and negative I rad 2. Do you want to do that? No. So, but anytime I could do it for any piece, I can get some values. And then my system of equations is much smaller than it would have been otherwise, because I figure out what the values are for certain letters. Okay, maybe. So go ahead and try to do 2e. Yeah. Yeah, that actually won. Totally. Yeah. No, it'll work. Both ways. So real quick, I think I talked last time about possibility, so let's make it official. All right, it's Thursday, you guys can take it off. Next Monday we'll include a review, so the test will be moved back a day, which, you know, really crams things up next week. So I'll have a test on Tuesday. Wednesday I'll have the test back to you. I'll give a practice final to you probably Monday. So on Wednesday I'll have the answer key for the practice final. Wednesday's review, and the final is on the frickin' Thursday right there. So, hello, summer.
Are we still doing those two sections in chapter 8?
More than likely, I'll just discuss them briefly. I won't make them do. That happens a lot. But, I mean, if you take Calc 2, they do a review of some of the stuff from those sections because you kind of build on it. And the ideas are pretty simple, but I'm just not going to make the homework do, obviously. We'll just talk about them so you have a bit of groundwork. Yeah? Yes. Will it be looked at? Maybe. So I don't know if you guys have noticed, I have been giving people back homework. Normally I grade the homework of the people who didn't do as well on the tests because they need some more help. If you give me the homework before the test, I try to get it done in time for you to look at. So I'm going to be giving homework back, some of it looked at, some of it not, right? And if you have any questions, you can obviously ask. Yeah. If I give you anything back, like a few days before the final, I'm not going to require you to do anything with them. Does that make sense? That's not fair, right? Okay. So I would give you full credit for it. I love it. And people are like, I could have just not done homework, just given it to them, everything in it. No, that's not how it works. Okay. So this problem, 6x plus 6 over, when you factor that, you get what? Where'd it go? Yeah, x plus 5, x minus 1. So that came from a over x plus 5 plus b over x. It does not matter which order this is in. If you put it the other way, my a will be your b and your b. Blah, blah, blah. Cool. My a is your b. So 6x plus 6 equals a times the other one. Good. Plus b times go. And then depending on the method you like better, you make a little system of equations, which is fine. If I were you, I'd rather do this every time I could. If x is 1, 12 is 6b, so therefore b is 2. If x is negative 5, negative 30 plus 6, negative 24 is negative 6a plus 0. So a is 4. Kicks ass. So therefore this becomes 4 over x plus 5 plus 2 over x minus 1. So then you get 4 ln absolute value x plus 5 plus 2 ln x minus 1 plus c. Sure. So just to continue to make this point, if I gave you this problem, You can factor the bottom, right? And then you could break it up. You with me? So it looks like the answer, though, this is the point I want to make. You could do everything we just did. That would be beautiful. That's the right way to do this. The wrong way to do this is to say this is the natural log of x squared minus 6x. Let's see. Right? I want that really out of here. It just drove me a little insane the last time I taught this. And I had stuff like the interval of 1 over sine theta. And somebody told me, well, that's the natural log of sine theta. And everything's easy. Everything's easy, Jeff. I don't know why people make such a big deal about this. Completely wrong. Completely wrong. There's no way. If you check it, what is it? It's missing. What should be, and let me see if you guys can get this. What should be up here so that is the answer? Does anyone know? There is something that would have been right here to make that the answer. Well, if this was the answer, the derivative would be 1 over this times 2x. If there was a 2x minus 6 up here, it's fantastic. It's got that chain rule piece that's missing that makes this not true. That is what u sub would do for us. If u equal this, its derivative is not in here. Therefore, it cannot be something that simple. It cannot be a one-step problem if the u sub doesn't work. It's got to be something a little more complicated. In this case, partial fractions would be needed. Like it. So please, dear God, if you're using ln a lot, there's a very good chance you're using it too much. Okay. Do you guys want to take a break right now? Okay, let's do that. Come back. Let's say 10 after.